Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're in a little mini series within that playlist that I'm calling Randomized Complete Blocks ANOVA. Now this is part 4 of a 6-part series, and we're going to look at estimability and contrast. Now the model, the Randomized Complete Blocks model, can be thought of this way, that y is equal to x beta plus epsilon, and then it can be partitioned into mu and x tau, part of the treatments, and then x beta, which is associated with the blocks, plus epsilon, where epsilon is normally distributed, mean vector 0, variance covariance matrix, sigma squared I. Now first let's look at estimability, but if you want as much detail as you need, I have a little 4-part mini-series on estimability where we go into great detail on what it means to be estimable. Essentially, it means that you can come up with a unique solution for what you want to estimate. And to me, actually, this estimability is quite fascinating, how it all works. And I won't go into it here so much, but it should be noted that the individual parameters, mu, all the taus in this tau vector, and all the betas individually are absolutely not estimable. Now, we can, if we introduce more constraints to this model, then we can come up with estimable, then these parameters are estimable, meaning we can come up with a unique solution. Now, what is estimable is the mean ij. So it's the mean of the I treatment jth block, which then, if you take the mean of this model here, then you get mu plus tau I plus beta. And it is estimable. Now, one criteria to be estimable. Remember, when you deal with estimability, you're taking linear combinations of the betas, right? So this is the beta, which consists of mu, all the taus, and all the betas, right? This beta star. Now we take a linear combination and of these betas, and so if we let lambda prime equal this, then this is estimable. And the reason is that this lambda is part of the row space of the design matrix, right? So if you think about this, we have a 1, lots of zeros, a 1, lots of zeros, a 1, lots of zeros. Somewhere this will fit in the design matrix, right? So the ones, there's always a 1. Now if we go over to the column associated with the ith treatment, then there's 1s, and then we have to go down to the jth beta. So anyway, so this is a row in the design matrix. So since lambda is part of the row space, then this is estimable, meaning we have a unique estimate for that. And to me, which is quite mind-boggling, because there is not a unique estimate for this beta star parameter. The least squares estimate, there's infinite number of those. But somehow we take a linear combination of non-unique estimates and they become unique. Anyway, that's why I find this little mini series so fascinating. So lambda beta is this is what we want to estimate. So lambda must be a part of the row space of x, which means lambda can be represented as row x, right? This is a linear combination of the rows, and this is for some row that's in AB space. So let's let rho be this. So it's all zeros except for 1, and then all zeros. And the 1 is in this position. And then the reason we do that, what that's saying is when we multiply this times this, it's going to pick off that row that corresponds to this lambda. That's what we just did. That's how we know that this is estimable. Now the unique least squares estimate of mu ij is we just plug in the least squares estimate for our beta, which is this. Now lambda can be represented by rho x. Least squares estimate for beta is this piece right here. X transpose x, generalized inverse, x transpose y. Now these x's form what's called a hat matrix, or M. It's a perpendicular projection matrix on the column space of X. Now it can be represented in this form, C part 2 and 3, in randomized complete block. Then when we take this Y vector in, we get the treatment mean, the block mean vector, and the grand mean vector. Then this row, which is this, so it only has a 1, all zeros and a 1. So when we take that times this vector, or let me do it here, this times this vector, then it picks off these. It's the ith treatment mean, the jth block mean, minus the grand mean. And this is our unique estimate for mu ij. And to me, that's crazy how that all works. Now, to get these individual parameters to be estimable, we have to introduce what's called a side condition, or side conditions. We assume that the tau's sum to 0, and we assume the beta's sum to 0. Then you mu, the tau's, and the betas are estimated. So in this equation, AB mu is equal to this. And you can kind of see it like this. If we take these sums into each of these components, then there's no index, so we're subbing it AB times. So this is already equal to that. Now here, if we sum over I, it's 0, and if we sum over j, it's 0. So these two are equal. But notice that this combination is an estimable function. So we divide both sides by AB, and then estimate this, and then of course sum over I and j. The estimate of mu plus tau I plus beta j is what we did on page 1. Now let's simplify it some. Notice that there's no j component here, and we sum over, from 1 to b, so we get b times it, of course the sum of I. Here there's no I component, so let's sum over the i's first, and of course j's left. Here there's no components, so sum over both, and we get AB times that. Now, of course, we carry the 1 over AB down, and then from here to here, it's the same. But this piece, now some do this so mindlessly, and I'm jealous that they can do it. I can't. So this is the ith treatment mean. It means that we've summed over blocks and then taken the mean. So if we unmean it, that means we divide by b, right? Divide by b and then take that away. But the b's cancel. And then we sum over I. So then we're left with y dot dot. That means we've summed over I and j. And here it's very similar. We've summed over the I component and then taken its mean. So to unmean it, we, 1 divided by a, y dot j is the same as this, but the a's cancel, and then we sum over the j component, and we get this. Here, to unmean it, we've summed over I, summed over j, divided by a times b, and then that's the mean. But if we unmean it, then the a, b's cancel, and we're left with just the sum. But those cancel, and then we're left with this, which is the grand mean. And that's a pretty good estimate for the mu, which is the overall mean. Now here, to find the estimate for the tau i's, we create this function. Now notice that we're summing over j. And so if we take the sum into here, we get b times mu, but then we subtract it, so that's adding 0. Here, there's no j component, so we get b of them, b tau I, which is what this piece is here. And if we sum over the j's, this is 0. But we have estimates for this piece, and we just developed an estimate for mu. So let's plug in our estimates. So divide by b to both sides, right? And we're left with mu, but we stick in our estimate. And here we stick in our estimate for mu plus tau I plus beta j. Now, the estimate is what we did on the first page. The ith treatment mean, the jth the mean of the jth treatment block, minus the mean, and of course minus that grand mean. But when we have to take this sum in, there's no j component, so we get b of them, right here. And here, if we unmean it, you know, if that's a word, 1 divided by a, and take away the mean, but then we sum over j, we get this piece. Here there's no index, so we just get b of those. Now let's divide the b in. Of course that piece carries down. Here we get the ith treatment mean. The b carries over. That b cancels. So that cancels with this. And then here we get the sum of the y's divided by AB, which is I should say that this cancels with that. And then we get the grand mean. And so this is our estimate of tau I. And similarly, we can do that for beta j. It's the jth block mean minus the grand mean. Now contrast, this is pretty fascinating. Unfortunately, we're not going to go too deeply into it in this video. But I'm going to point you back to previous mini-series where we go in great detail, and I find it quite fascinating. So we're only interested in the treatment contrast, right? Why do we want to estimate the blocks? I mean, that's, you know, usually of no interest. So gamma, which is our contrast in the taus, if and only if gamma is equal to the sum of these. So it's a linear combination of the treatment parameters, but in a way that the CIs have to sum to 0. Okay. Now, if we think about it in, you know, vector notation, it's going to be lambda I times beta, right? A contrast, you know, something that we want to estimate is a linear combination of these beta parameters, right? But to be a treatment contrast, lambda has to be of this form, right? So if we take this lambda times beta, it doesn't pick up the mu parameter, and it doesn't pick up any of the beta parameters. It only picks up the tau parameters, right? And of course, this lambda has to sum to 1 or 0. That's why we have this. But to be estimable, this lambda parameter has to be a part of the row space. So there has to be some row, you know, so where rho prime x is equal to lambda. And this is for some row in AB space. Well, it turns out that we construct contrast and orthogonal contrast and partition the treatment sum of squares similarly as we do in the one-way fixed effects ANOVA model. And actually, we developed this in the repeated measures one-way fixed effects ANOVA. We went in great detail how to calculate these contrast, the treatment contrast. And so I'm going to point you back to the 2 previous mini-series on much more detail on these treatment contrasts. Of course, we'll cover this in the R software part 6 too. Well, this is all I have for this video. Hopefully you enjoyed that. I sure did. Now the next video is we're going to assume that the treatment effects are random. And these videos, up to now, we've assumed that they're fixed. So I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.